All right, so we're going to talk about production and costs for an individual firm. Big picture, we're getting to the point where we want to solve the profit maximization problem for an individual firm, choosing how many units of output to produce a given period, what price to charge in order to maximize profits. So previously we talked about our definition of total costs of the firm as implicit versus explicit, giving us our specific definitions of profit as being either accounting profit, only accounting for those monetary or explicit costs, or what we're focused on, economic profit that includes opportunity costs or implicit cost of production. So now we're going to continue along that kind of path and thinking about how to construct a function that relates total cost of production to output with the assumption that we're including those implicit costs in that calculation. So this next way to kind of disentangle different types of costs rather than implicit versus explicit, now we're thinking about long run versus short run and how the relationship between cost and output changes depending on the time frame of observation. Right? So that's kind of the first note that we're making here. So again, TC sub I is the total cost to produce a given level of output for one individual firm indexed I. So we have a very specific definition here of short run versus long run. When we talk about a short run cost or short run production, what that means is we have a time period short enough that we don't have time to change all of the things that we might want to change from the point of view of a producer. So if we want to increase output, we would like to be increasing all of our inputs. But in a short time frame, we don't have the ability to change our capital input. We can only change our labor and raw materials. So half the battle here, as always, is with the notation. So when we're talking about capital, K, that represents the size of our factory, right? The level of machinery that we have access to. Labor, L, of course, is hours of labor, hours of person work hours that we have access to. And while this is not always true, of course, it's easiest to think about this as the case where our capital, access to capital is through a rental contract, right? So imagine I'm operating a restaurant. I have a 8,000 square foot restaurant somewhere in San Francisco, but I don't own it, right? Somebody else owns it. I rent it from them and I sign a lease every year, right? So I'm going to pay the same rent and I'm locked in for that year. That is my short run. Right? And it doesn't have to be contractually obligated. It can just, kind of factor in the idea that it takes time, it takes resources to make changes in those kind of large scale uh, capital purchases. Okay. So yeah, so here's the example. If my pizza restaurant experiences a doubling of demand, could happen. I'd like to move into a larger restaurant space immediately, but I can't, right? I've signed the lease. It's going to take me time and effort to find the perfect space. In the long run, I might be able to do that, but if just because a busload of tourists come by and they all want pizza, I'm not going to move into a bigger restaurant to accommodate them. I can bring in additional workers for that day or have people work overtime for me. So labor is a lot more flexible than capital. That's the main point we're trying to get to here. So in the short run, labor is flexible, capital is fixed. Now, the reason why that's relevant to our current discussion is when we think about the costs of production, they are going to, right, the payments for those inputs, labor, raw materials, or capital. So some of those costs will be changing as output changes in the short run, labor and raw materials, and some of them won't. Those are going to be our capital costs. So this gives us a nice, easy distinction here when thinking about our costs. Costs in the short run that don't change, that have to be paid no matter what the level of output is, That's going to be our fixed cost. And again, we're going to attach that to payment for capital. And we will denote that as TFC. So any costs that don't vary with output in the short run, capital costs or fixed costs. And when we say costs that don't vary with output, well, that also includes when output drops to zero, right? So again, in my pizza restaurant example, if demand collapses and I go out of business, I'm still contractually obligated to pay those costs, right? I still have to pay the rent for my factory. So at zero or maximum output, doesn't matter. Those costs are going to be the same. And as always, we need to have a visual mathematical representation of these relationships. And I like to say this is going to be our easiest graph, right, in the chapter in the semester, plotting costs versus output. If we're only focusing on our fixed costs, well, the word fixed does a lot of work there. That doesn't change, right? So whatever the dollar value is here, dollars paid per week, per month, etc., during that short run, output goes up and down. Output can be at zero. Cost doesn't change. Okay, so it's just going to be dollar value of expenditures on the vertical, quantity of output on the horizontal, and then the function itself is just that straight horizontal line. Same cost at all levels of output. Now, what we'll get to a little bit later is, in the long run, if I moved to a new facility that had a higher rent, well, that whole thing would shift up for my next short run period. Or if I moved into a smaller facility, that might shift down. But during the period of the short run, which is where we're operating, it's going to be this fixed value. So that brings us to the more difficult of the two components, are variable costs. So the terminology here is, again, pretty straightforward. Fixed versus variable is in reference to changes in output, right? So in the short run, the only way to increase our output is to hire more workers, right? And those workers don't work for free, so we have to pay them their wage. So output rises, forcing labor input to rise. That forces our costs associated with labor to increase. And that, again, is our variable cost. And using similar notation, our total variable cost, TVC, there's other things associated with it, but easiest to think about this as our costs combined with or associated with labor inputs. So now, here's the tricky part. We know that as output increases, labor increases, so our variable cost will go up, but the rate at which those costs rise, exactly how those two things are related, requires a little bit more discussion. Okay? Well, it's not that hard, right? It depends on when you hire that extra worker, how much extra output do you get from that worker? How productive is each worker? What are you getting for that wage that you pay? That's going to translate into this cost relationship. So we have to take a little bit of a detour here before we bring it back to that cost function. And we have to focus on this relationship between labor and output, giving us our labor productivity. And luckily, there is a very straightforward and well-established mathematical relationship between these two things, labor input and output in the short run. And that is what's known as the production function. That's the mathematical relationship. And the pattern follows the law of diminishing returns, which we've seen in the context of consumption and utility. The law basically works the same way in terms of production and productivity. So first of all, definitions. The mathematical function relating output to labor in the short run, so when capital is fixed, is our short run production function. And when you think about, again, life as a producer, whether you're running a factory or whatever the case may be, this is information that you need to know, right? You need to be able to predict how many units of output you'll be able to produce and put on the market when you hire 10 workers, 20 workers, 30 workers, right? You need to know what those values are going to be. In strictly mathematical terms, we can express this production function idea as Q equals F of KL. Output is a function of labor and, sorry, K, capital and labor input, with that distinction that capital is fixed, right? We have only so much square footage, only so much machinery to work with in the short run, and we let our labor go up and down to influence output. So that F again represents some mathematical function. And what's going to be driving the behavior of that function is, once again, diminishing returns. So specifically, diminishing marginal returns to labor. Again, the terminology here is going to sound very familiar from our utility discussion. Past a certain point, each additional unit of labor adds less to total output than the previous unit. For each delta L new worker hired, delta Q gets smaller and smaller and smaller. They get less productive, add less to the total output. Again, on the utility side, this was each additional cookie that you eat adds less total happiness past a certain point. Same idea. Being driven by a slightly different scenario here. Right? What is it about those added workers that makes them less productive? Is it because they're less well trained? They're not working as hard? They're lazy? What's going on? Well, no, it's the definition of the short run. It's that we're adding more and more workers to the same amount of capital, the same amount of space, right? So kind of think about it in the extreme. You're you're jamming this extra worker into an assembly line, and they have to squeeze in next to somebody else, and they don't really have a lot to do, right? All the machinery is already being used. They might add a little bit of extra output, but they can't be that productive through no fault of their own just because they don't have the capital to work with. So it's this short run assumption of fixed capital that makes each additional worker past a certain point less and less effective. So we'll see this as this ratio of extra output to extra worker decreasing as we put more and more workers into the process as labor input increases. So, which gives rise to this definition. So that ratio of extra output per extra worker has a name. It's the marginal product of labor, right? Again, on the utility side, we focused on marginal utility. Here it's marginal product. And from a supplier's point of view, an owner, a manager of a supplier, you need to know this, right? When a worker walks in the door, you don't think, oh, there's Joe or there's Pamela. You think there's 4.2 extra units of output per hour, right? What is that worker's marginal product of labor? What are they going to give to this process? That's what we're calculating here. Units added per additional worker. And likewise, as a worker, you want to typically maximize this value as well, be as productive as possible to earn that raise, et cetera, and keep your job. But from a mathematical relationship standpoint here, when we're talking about diminishing returns, we're talking about falling values of marginal product of labor. Holding that capital constant, this measure of labor productivity is going to start to fall. Just as a side note here, the OpenStax microeconomics textbook does use the notation Q for output, also refers to it as TP or total product. They mean the same thing. It comes up in its calculations and equations. You'll see that other places as well. So, what is this production function going to look like? It might look something like this. So, always nice to throw some numbers at it. So, what we have on the left here, just a little table, labor and output, and the associated marginal product of labor. So, again, just to stick with our kind of silly example, when we think of that labor column, that's how many workers I have in my pizza restaurant at any given time. And quantity is number of pizzas that we can produce in a given hour. So, of course, if nobody's working, even if I have the most beautiful capital equipment, the great kitchen, great square footage, but there's nobody there to work, we get zero output. So I hire the first worker, and let's suppose my total output goes from 0 to 8. Well, that worker has added 8 units of output. So their marginal product of labor for that first worker is 8 units. Nice job. We hire the second worker. Delta L is 1. Output rises from 8 pizzas per hour to 18. Well, from 8 to 18 has added 10. So that second worker has an MPL, marginal product of labor, of 10. And so on down the line. The third worker raises total output from 18 to 30, so they add 12. We'll get to what the pattern of the numbers actually is in a second, but just for the calculations, the fourth worker, total output goes from 30 to 40, so they've added 10. Fifth worker, 40 to 48, they've added 8. No stopping us now. From 48 to 54 for worker number 6, they've added 6 units, and then that gap between worker 6 and 7, raising output from 54 to 58, they've added 4 units, so that is their marginal product. On the right, what you see is, as advertised, right, the mathematical relationship between labor and output when capital is fixed. We've just plotted all of those points, right? So worker number 1, total output is 8. Worker number 2, total output 18, 3, 30. Worker number 4, 40, 48, 54, and 58. So just plotting those points, connecting the dots, we get this. It's kind of hard to pick up in this graph, but you do see that it's a non-linear, kind of a wave-shaped pattern in this resulting function. It turns out that non-linearity tells the story of the law of diminishing returns to labor. Okay? So let's kind of zoom in on those first 3 workers. And of course, what we saw is that output was rising, of course, right? The more workers, more output, but it was also rising at an increasing rate. So kind of the opposite of diminishing returns. Each additional worker adds more to total output. So on the graph, when we're plotting out those points, right, each movement to the right is the delta L of 1. Then the marginal product, the change in output, right, is our delta Q. So the ratio delta Q over delta L, in this case, is just 8 to 1. And that's what's increasing, right? So the next worker adds a little bit more, so it steepens that function. The third worker adds 12, gets a little bit steeper still, so it gets hard to pick up in the graph, but the slope of that function is the marginal product, and it's getting steeper and steeper. So again, what that tells us is that rather than what we might have been expecting right off the bat of diminishing returns, we actually see this period of initial increasing returns. So what's happening here? Again, it's not so much about the quality of the workers. It's that we have plenty of capital to go around, right? We're going from 0 to 1 to 2 to 3 workers, right? So they're not running into each other. They all have their own little space. So that capital constraint really isn't binding at this point. But there is going to be gains from specialization. So again, it's a silly example, but just think about what would be happening if we had just one worker in our pizza restaurant. Right? They would meet the customer at the door, they would take them to their table, they would take their order, then they would run back in the kitchen and they would make the dough and they would make the pizza, and then they would cook it, and they'd bring it back and they'd get the drinks. They'd be doing everything, they'd be running all over the place. They could really use some help, right? So if we brought in a second worker, rather than running into each other and having diminishing returns, the gain is going to be greater. Out, the labor input doubles from 1 to 2, but total output more than doubles. So now nobody's running around having to do everything. We have specialization, we have specific areas, we have specific jobs that each person does. And we're going to get continual gains along those lines. There's that phrase again, up to a certain point. Right? And in this case, that certain point is worker number 3, right? That's where we saw maximum marginal product of labor. After that, it starts to fall off. So we have a specific term for when that switch happens. We're going to call that the inflection point. And we, of course, borrowed that from mathematics. You may have heard that from calculus. So when the second derivative of a function changes sign, when a function goes from getting steeper and steeper to flatter and flatter, increasing slope versus decreasing slope, or vice versa, that's an inflection point. And that's what's happening here. Our economic interpretation of that is that that's the point where diminishing returns begins. Past that point, each additional worker adds less and less. Why? We've exhausted the gains from specialization and run into the problem of fixed capital. Now that extra worker, yes, is helpful, but not as helpful as the previous. So marginal product falls, and the slope of that production function starts to get flatter. So focusing in on those additional workers past worker number 3, which again, we can locate that inflection point by calculating the marginal product. When the marginal product is at its highest value, that's the inflection point, because each worker past that, at one extra worker, adds less and less. So the third worker added 12, the fourth 10, then 8, then 6, then 4, right? So those delta Q values for each delta L get smaller and smaller. So we get that flattening of the production function. So that is the typical pattern that we're going to see in the short run. Again, all of this is under the assumption, the crucial assumption of fixed capital. It's in fact easier to see where that inflection point occurs if we actually just plot, instead of total output, we plot the changes. We actually plot our labor productivity or our marginal product of labor. So now we're saying that first worker added 8 units, the second worker added 10, the third added 12, and then we're decreasing back to 10, 8, 6, and then 4. We're on the down slope here. So plotting the marginal product of labor gives us our labor productivity for each worker, and again, makes it much easier visually to see where that inflection point is. We still call it the inflection point, the point of diminishing returns. So thinking ahead to like homework questions and exam questions, quiz questions, if you're given a column of labor and output, be able to use that to calculate marginal product, be able to locate the inflection point, be able to talk about why the numbers change the way they do, and be able to draw a plot like this, the marginal product, and the production function as well, that matches the numbers that you see. So in general, just to make it a little bit easier to see what's going on, if you're asked to sketch out a production function, it would look like this. It's the same as what we saw before, just a little bit more dramatic in the visual. getting steeper and steeper and steeper. As labor increases, each worker gets more and more productive until the inflection point comes around. After that, now we've run the course from those gains from specialization. Capital, fixed capital constraint is binding, and workers become less productive. So up until the inflection point, we get increasing returns. Past that point, we are in the realm of diminishing returns. And that's never coming back, right? It's, in other words, it's never going to see another period of increasing slope. It's basically just going to flatten out. And in fact, eventually it's going to start to come down, right? That you can have not only diminishing returns, but decreasing output. That's that extreme case where again, you force one more worker into this fixed space and they actually cause everybody else to be less productive. That's typically not a realistic scenario, but hypothetically, that is possible. So now, remember, that was, in a sense, a detour, very important detour, but a detour nonetheless from our discussion of costs and profit. So the last thing we're going to do here is make the translation from labor productivity into dollars spent per unit produced. Okay? So once again, thinking about these variable costs, right? As we're moving along that production function from left to right, output is increasing because you're hiring more workers. Well, again, each worker is adding to our total cost, right? Each worker is being paid some wage rate in our pizza example, right? So how $20 per hour per worker, variable cost rises the same amount relative to labor. Each extra worker adds the wage rate to our cost, $20 per hour, for example. But when we plot it against output, each additional unit of output requires a different amount of time to produce, a different amount of labor input. So that change is going to be different based on labor productivity. But luckily, we've already got this all sorted out, right? It all depends on where you are in that production function. Are you in the increasing returns portion to the left of the inflection point, or have you hit the inflection point and are experiencing diminishing returns? So starting from, again, left to right, at those low levels of output, we haven't hit the inflection point. We're experiencing increasing returns and everything's good, right? Each additional worker adds more to our total output, both marginal product of labor and therefore the change in output are rising. So what does that mean in terms of costs? Since each worker gives you more output, each unit of output requires a smaller increase in costs. A smaller portion of an hour is used to produce that output. So what that means is our variable cost, our labor costs, are rising, but at a slower and slower pace. It's exactly the mirror image of the production function. As labor gets more productive, the output they produce is less costly on an additional unit basis. So when we saw that production function get steeper and steeper, what we're about to see, this cost function gets flatter and flatter. But those good times only last so long. We hit the inflection point and all of that flips around. Once we hit the inflection point, we're in the realm of diminishing returns. Each worker adds less total output. Each unit of output requires a higher increase in costs. So as output increases, costs now begin to rise at an increasing rate. The function becomes steeper and steeper as the production function gets flatter and flatter. Right? They're just two sides of the same coin. One is in output terms, the other is in dollar terms. So if we plot that out, once again, it's all based on where we are relative to that inflection point. So now we have, note that when we're doing these cost curves, just like we did with that fixed cost line, right? It's plotted against quantity, against output. And here we're going to have our variable cost, our TVC in dollars, plotted on the vertical. So as advertised, to the left of the inflection point, output's rising quickly, costs are rising more slowly. Once we hit the inflection point, labor is less productive, costs are going to rise at a quicker pace. Also note that the variable cost curve does have a value of 0 when output is 0. Not the case with fixed cost, right? So here, if you're not producing anything, you can go ahead and, for the most part, fire all of your workers, right? I don't. In reality, it's not that easy. There are legal protections, but for simplicity purposes, think of it that way, right? We totally shut down. We send all of our workers home. We're not paying them anything. That's where we start here at 0, 0. Then, as output is increasing, costs rise at a diminishing rate, hit the inflection point, then rise at an increasing rate. So we don't see it directly here because it's output versus costs, but what's driving this behavior is diminishing returns. The law of diminishing returns to labor, the shape of the production function, directly translates into the shape of this cost curve. More productive labor, slower rise in costs, less productive labor, quicker rise in costs. Okay, that was the hard part, right? Now we're almost there. Remember how we started this off? What our goal was to find a mathematical function that relates output to our total costs, which we can then combine with our total revenue to get profit. Hey, we've done it, right? So the two components of our total costs we have now defined, right? Our total fixed cost, that straight line as output increases, our total variable costs increasing at a decreasing rate, hit the inflection point, then increase at an accelerating rate. Well, we just have to add those two together, right? Because what is our total cost? It's just the sum of our fixed and our variable. So basically what this graph does is at every level of output, we take wherever our variable cost is, and we add our fixed cost to it. We basically shift that whole thing up. The distance between variable and total is just the amount of our fixed cost, right? So we're just adding that value. So we note that when output is 0, labor costs are 0. So all of our costs are fixed. So that's the starting point of that total cost curve. And then the shape of total cost as output increases is just exactly reflecting those variable costs because it's just that whole function shifted up by the amount of our capital or our fixed costs. But once again, when you see that total cost curve shaped the way it is, and you are asked, hypothetically on an exam, why does it look like that? The answer is the same. The law of diminishing returns to labor. That's why the production function looks the way it does. That's why the marginal product of labor curve looks the way it does. That's why our variable costs behave the way they do. And that's why our total cost looks the way it does, why it has that shape. It's all because of diminishing returns. So what comes next is translating this one more time into a dollars per unit calculation, averages and marginals. We'll look at some numerical examples of that, filling out a full cost table and plotting it all out. Then we'll be all set to go back and focus on the revenue side, which will depend on the level of competition in a given industry and how price and quantity relate on the demand side. So until then, enjoy your production and costs, and I'll see you next time. Thanks.